Great, thanks so much. Yeah, I'll be talking about self-supervised learning for autonomous driving. That title sounds similar to what some of the general themes that Wolfram talked about this morning, but kind of different specific methods. I'm David Held. I'm an assistant professor at Carnegie Mellon University. So first let's just start with why is autonomous driving so hard? When most people start working on autonomous driving, or at least when I started working on it, 10 years ago now, I think, people typically think about something like this. You think, okay, you just need to follow the lane and make sure not to hit other objects there and whatever car is in front of you. So it seems pretty easy. Why don't we have autonomous cars now? Well, first of all, not all driving looks like that. There's driving at intersections that get a little bit more complicated. You have to think about rights of way and whose turn is to go. But it actually gets even more complicated than that. Here are some pictures from Tesla of weird things that they've encountered on the road. So we see a chair flying off the back of a truck, a dog running next to a car, a highly reflective, a vehicle with a highly reflective surface and cones on the side. And so there's all sorts of things that, if you just do a drive to and from work, you might not see these every day, but you'll see some weird things with a reasonable frequency if you do lots of driving, and autonomous vehicles need to be able to handle this. So essentially, I'm thinking about the long tail of autonomous driving, where we have the common events that where driving is pretty regular and easy. But then there's the more difficult situations, and then also the weird situations that our autonomous vehicles need to be able to handle as well. And so this is another slide from Tesla's talk, which says it's all about the long tail, and it shows kind of a spectrum of increasingly weird events that they've encountered on the road that autonomous vehicles need to be able to handle. So how can we handle these? Well, the traditional approach to learning, machine learning, is a supervised learning approach where we have some large image data set of data collected from our autonomous vehicles. We feed that to a human labeler that labels this data. The labeled data gets fed to a machine learning algorithm, which outputs its predictions about where objects are in the environment. And this can be used by an autonomous driving system to avoid crashing into other objects. But the problem is, how do we ensure that we've actually gone through and labeled all of these weird cases? We can maybe collect lots of data that has, we can collect lots of data relatively easily by putting sensors on vehicles and driving around, but only a small fraction of that data will actually have these unusual events. And if we rely on human labelers, we might not be able to label fast enough to cover all of these unusual cases. So to really scale up autonomous driving, I think we should break away from the supervised learning paradigm and go towards self-supervised learning. So if we imagine we just have a massive amount of unlabeled data, how can we use that unlabeled data to improve performance of autonomous vehicles and handle increasingly strange events on the long tail? So I'll be talking about a few different methods for self-supervised learning for autonomous driving, starting with actually the first project I'll talk about is not actually about self-supervised learning, but it's about low-cost sensors. And then I'll talk about two approaches to using self-supervised learning for different types of tracking methods. So I'll begin by talking about some work that I've done recently on active perception with light curtains. This was presented at ECCV this year, and this was work led by my student Sid, shown, this picture is shown here. So if you think about what kind of sensors people use for autonomous driving, the most common sensor is to use a LiDAR, such as a 64 beam Velodyne LiDAR, and a Velodyne LiDAR records the depth of points in the scene, which is very useful if you want to make sure that you don't crash into objects. It's useful to make sure you know how far away objects are from you. And so LiDAR is very popular for those reasons, but it has some limitations as well. As you can see, it creates this sort of sparse point cloud. You can see the rings created by the LiDAR sensor, and essentially you can't see the data in between those rings. And additionally, it's very expensive. So a Velodyne 64 beam LiDAR can cost over $80,000. And so it's hard to make affordable autonomous vehicles using this device. So on the other hand, there's a device that was developed at CMU known as an active light curtain. And the idea is that you can use a light curtain to sense a certain part of the space where you decide that you want to sense. And wherever you choose, you get a dense point cloud in that region. And so that fixes the sparsity problem. And it's also very affordable. So our lab built prototype costs about $1,000. So this can help to enable affordable autonomous vehicles. So what is a light curtain? So a light curtain, you can see the lab prototype shown here. Essentially, the main components are a rolling shutter camera and a laser that's connected to a galvo mirror. And the laser projects light onto a scene in a given plane, and the rolling shutter camera perceives light in a given plane. And where those two planes intersect, that's the location at which we're going to sense the depth. So we sense whether or not there's a point at the intersection of these two planes. And that tells us some sparse information about the depth of the scene. So essentially, the idea is you can rotate the galvo mirror to point the laser at different locations. And based on how you choose to rotate it, you can trace out this curtain profile shown here, where you choose these control points where you want the laser and the camera to intersect. And these are the points at which we'll be sensing the depth of the scene. So we'll only know the depth, we'll only know whether or not there exists a point on the surface of an object at these control points. And we don't know the depth about anything else. So we essentially get more or less binary values. Is there a point at these control points? And we don't know anything else about the depth of the scene otherwise. So here's a visualization of what this looks like. So on the left, I'm overlaying the LiDAR points shown in white with the light curtain that's shown in blue. And the green points indicate the points where I've sensed the depth. And this light curtain is moving in a certain pattern, but that pattern could be different. This is just some pattern, but the pattern gets chosen by the algorithm. And on the right, you can see the same thing in image space, where we're visualizing which points are perceived by the light curtain. So the next question is, where should we place the light curtain so where do we want to try to sense the depth of the scene? And so our strategy is as follows. We start with a single beam LiDAR, which is a relatively affordable depth sensor, but it just records the depth in a single plane of the scene. So that gives our initial sparse points, and we feed these points to an object detector, which is going to output some initial detections with a confidence score for each detection of how likely that box is to contain an object. Then we take the confidence scores and we normalize them to be numbers between 0 and 1 that we treat as probabilities. And then we compute the entropy of that probability to get a measure of the uncertainty of that point. So essentially, if the probability is close to 1/2, then there's high uncertainty. And if it's close to 0 or 1, then there's low uncertainty. So then we take all those uncertainties and create an uncertainty map. And then we place a light curtain along the regions that have highest uncertainty in order to get more 3D points that we feed back to our 3D detector and then we can repeat the process over and over again to continue to improve our detection performance. So there's a caveat though, it's not quite that simple, which is that the light current has physical constraints. So remember, the way that you choose how the light current gets created is by rotating this galvo mirror that decides where the laser and the camera intersect. And the galvo mirror has a certain speed, a certain maximum speed that it can rotate at. So based on that maximum speed, that determines how far apart two consecutive points on the light current can be. So now we essentially have a constrained optimization, which is that we want to place a light current in a place that maximizes the sum of uncertainties. We formulate this as saying that we want to maximize the information gain, meaning we want to get the most information out of the light current relative to the information that we had before, subject to the light current constraints, which constrain the set of curves that we can trace out. So now we have this constrained optimization, and the way we solve this optimization problem is we formulate the constraints via a constraint graph. So the black nodes here indicate all the possible control points that our light current can pass through. And for each pixel ray of the camera, we need to pick one point that we're going to choose as our control point. And the way we formulate the constraints is through edges in the graph. So if we are, for example, at this point, at a given time, so say this point is the current intersection of the laser and the camera, then in the next time, the galvo mirror can move such that the intersection of the laser and the camera are any of these 3 points, but not any other points. So these edges constrain the possible light currents that can be traced out by our device. And so now we just need to find the path through this graph that optimizes the information gain, because the graph already encodes the constraints. And so we solve this efficiently using a dynamic programming approach, starting from the rightmost pixel ray going all the way to the left. So here you can see what that looks like. This is a top-down view of a scene where I'm painting the uncertainty with white as highest uncertainty and black as lowest. And this is the light current path that was found using our dynamic programming algorithm. So you can see it passes mostly through the high uncertainty regions while obeying the constraints of the light current device.
So we have a question.
Yeah.
Yamin Lee. Yimei. Yeah.
Oh, I see the question in the chat. Yeah. So in the light current method, how is the uncertainty map computed? By simply accumulating entropy at each pixel of the image. So no, so let me go back. Okay, so we're not operating in image space. I showed images before just for visualization purposes. We're operating purely in point cloud space. So we start with the single beam LiDAR, which gives a sparse set of points, and then we get our initial detections. And then the way the uncertainty map is computed is you imagine a bird's eye view of the scene, and at each you can divide up the bird's eye, essentially the plane of the scene into a grid, and at each grid point, you look at the detector output to get the confidence score of an object being centered at that grid point. And that confidence score is converted to a probability, which is converted to an uncertainty. So let me know, Yiming, if that answers your question.
We have another question. Yeah.
Yeah. So yeah, and the other question is the latency of the both detection under the LiDAR model and adjustment and application of the light current. Yeah. So latency. is a question we looked at but didn't fully address. So our method, because we use dynamic programming, the light current optimization is very fast. The part that takes the most time is actually the feed-forward pass through the network, which, if it's a very deep network, there could be some latency. And if the objects are moving very fast, then we would need to take that into account. So actually, we're currently working on a follow-up project to try to account for the latency by essentially trying to predict the velocity of the objects and use that to adjust the light current placement, considering the amount of latency in the system. So yeah, let me know if that, awesome. Okay, cool. Yeah, if there are any other questions, feel free to type into the chat or click the raise hand button. Okay, so here's, right, so that's our method. And next I can talk about the results. So here's an example of a scene where we're trying to detect these objects. Now we start with our initial single beam LiDAR, which gives just these sparse points shown in green, and I visualize the uncertainty map underneath shown in gray. And on the right, there's a scene again, just so you remember. And so you can see that there's a missing detection because these initial light current, initial points from the single beam LiDAR are very sparse. So then we place a light current shown in blue, and that gives us these additional points shown in green that we feed back into our detector, which allows us to detect the objects shown here. So here's kind of what that looks like dynamically. So on the left, I'm showing all the different light current placements. And on the right, I'm showing the scene that we're building up over time. And you can see that after just one light current placement, we're able to detect the object that was previously missing. Here's another example where we have a scene with a bus in it, and we're running our car detector, which mistakenly detects the front of the bus as a car, and also this patch of grass on the right is also detected as a car. So we have these two false positive car detections. We run our light current to collect more points, which removes the false detection on the left. And then after one more light current placement, we remove the detection, the false positive detection on the right as well. So here's the dynamic view of that. On the left, again, you can see the different light current placements. On the right, you can see the accumulated points of the scene. Here's a last qualitative example. So here's a vehicle, and we run our detector from the single beam LiDAR points, and you can see it's misaligned compared to the alignment of the ground truth. And after running a light current, placing a light current, we are able to correctly detect the alignment of the vehicle. So how does this evaluate quantitatively? So we compare our strategy for light current placement to 7 other strategies shown here, and you can see the performance of all of them. So we came up with a range of different strategies to compare against. Placing light currents always at a fixed depth, placing it at random locations, using a greedy optimization instead of dynamic programming. Here's the performance of our method, which you can see significantly outperforms all of these other strategies, which shows the benefit of our approach of incorporating uncertainty and optimizing with dynamic programming. And here you can see that as we add more light currents, our performance improves. And if we add even more light currents, including a number beyond the amount that we trained with, so we train only up to 3 light currents, but at test time we can place many more light currents, and the performance just continues to improve, showing that our method generalizes well to an arbitrary number of light currents. So to conclude this part of the talk, we have proposed a method for active detection using light currents for autonomous driving. We optimize the light current placement by encoding the light current constraints into a constraint graph, and then using dynamic programming to optimize the objective. And we show that our method can improve detection accuracy, and the general motivation of using light currents is to make affordable a depth sensor system, with a caveat that you have to use an algorithm to figure out where you want to sense, and that's where our proposed method comes in. So that's the first part of the talk. If there are any other questions about light currents, I can take them now or also at the end as well. So I'll pause for 1 second to see if anyone else wants to ask a question. Okay, so that was the first part of the talk on active perception with light currents. And next, I'll talk about our work on self-supervised 3D scene flow. And this is work done with my students Hamangi and Brian, shown here. So, okay, so let's talk about how tracking traditionally works in autonomous driving. So traditionally, you have this pipeline for tracking where you take as input a stream of 3D data, you run a segmentation or object detection method to find the objects in the scene, and then you track these objects over time and estimate their velocities and use this to predict the future motion of each object. And based on that future motion, the autonomous vehicle can plan its trajectory to try to avoid colliding into any of these moving objects. Now, the problem with this pipeline is that suppose that you have a tracking error. So suppose that all of these objects, for example, these people maybe are grouped standing very close to each other. So maybe our detector thinks that they kind of look like a big car or something like that. Now, the reason that's a problem is that if some of these people have a different motion than the other people in the crowd, well, we're not going to be able to detect that because the tracking method typically assigns one predicted velocity per object. And so if these people are all lumped together as a single object, according to our detector, then we won't be able to notice that this person is moving differently from the rest of the crowd. And that could be dangerous if that person is about to walk into the path of the autonomous vehicle. So the fundamental problem here is that we're operating at the level of objects. And if you make a mistake about where the objects are, you might make a mistake in terms of tracking and prediction, which can be very dangerous. So we were looking at an alternative approach, which is to look at 3D scene flow. So scene flow estimates the motion of each 3D point in the scene. So it's kind of the 3D analog of optical flow for those who are familiar with that. And this can be much more robust because it doesn't rely on object detection or segmentation to make these predictions. It just looks at the raw point cloud. Now, I'm not saying we shouldn't use any notion of object detection in our autonomous driving systems, but scene flow can be a good thing to incorporate to make your system more robust to detection failures. So how are we going to predict the scene flow? There's traditional registration approaches, but those typically depend on the initialization and don't always work perfectly. Recently, there's been a number of approaches using deep learning for scene flow, which have better empirical performance on a number of metrics, using a neural network to learn to predict the scene flow from a pair of point clouds. And the advantage of that approach is that they can predict very accurate scene flow. The downside is that they require point level motion labels to train. So since you're predicting scene flow, meaning you're predicting a motion for each point, you need a ground truth, which includes a label of the motion of each point to train these methods. So what we asked in our research is, can we learn scene flow in a self-supervised way from unlabeled data? So here I'll present our method for learning scene flow from unlabeled data. The way it works is as follows. So suppose you have two consecutive point clouds shown in blue and red. And now we're training a method to predict the scene flow. So we pass these point clouds through our network, and our network is going to try to align them. And now we put a loss on the output, using a nearest neighbor loss. I'll explain in a second what exactly that is, but I'm just starting with the high level picture. And then we take the predicted output and the initial frame, and we try to predict the reverse flow back to the original point cloud. And so now we have a cycle, and so we use a cycle consistency loss on that part of the flow. So these two boxes here where it says forward flow and reverse flow, those are actually the same scene flow network, just with different inputs. And so this loss is used, both of these losses are used to train the same network weights. Okay, so what are these losses that I'm referring to? So the first one is the nearest neighbor loss. And the way it works is, given these 2 point clouds, suppose that I have some point X and I want to compute the flow or the motion of this point, where this point moved to in the next frame. So suppose that my network predicts that the point moved here. So that's the guess. It's not correct. The ground truth point is somewhere over here, but we don't know where the ground truth is because we're talking about learning from unlabeled data. So what we can say, though, is that this point, we can look at the nearest neighbor to that point in the next point cloud, which is this distance. And so at the very least, we should hope that if our scene flow network is doing a good job, it should output some point that's near some other point in the next point cloud. Ideally, it should be near the ground truth point, but at the very least, it should be near some point. Okay, so that's the nearest neighbor loss. It just minimizes the distance between the predicted location of where this point is moved to in the next frame and the nearest neighbor. So now nearest neighbor loss doesn't work by itself, because suppose you map all the points in the first frame to the same point in the next frame, the nearest neighbor loss would be 0, and but that's not the correct solution. So we also add a cycle consistency loss. Now we take this predicted point and we try to map it back to the first point cloud. And now we actually know the ground truth of where this should map to. It should map back to the original point where we started. So that's our cycle consistency loss. And that has a degenerate solution as well. If you just predict that none of the points have moved at all, then you'll get a perfect cycle. So we have 2 different losses. They each have a degenerate solution, but their degenerate solutions are different, which means that you can't optimize both of these losses with a single one of these degenerate solutions. Ideally, the network learns to output the actual ground truth flow in order to find a better way of minimizing these losses. So those are our 2 losses. Now there's one other thing we had to do to get this to work, which is as follows. So remember I talked about the cycle where we predict a point cloud and then we feed in the predicted point cloud back into the network to make a cycle back to the original frame. Now, the issue is that at the end of training, maybe our predicted point cloud looks very nice, like a transformed version of the original point cloud, but at the beginning of training, it doesn't look very good. You get a predicted point cloud, which is just a big mess of points. And now if you take this mess and you feed it back into the network for the reverse direction to compute the cycle consistency loss, then you'll essentially have a garbage in, garbage out situation, and the learning will be unstable. So in order to stabilize our training, we do what we call anchoring, which is we take our predicted noisy point cloud and we find the nearest neighbor on the point cloud that we're trying to align to, and we move the points some fraction of the way towards that nearest neighbor. So we're kind of anchoring the points towards reality. And now we feed in that anchored point cloud into the network for the reverse flow. And then now we can try to align that and get a much more reasonable prediction. So that's our method. We have nearest neighbor loss, a cycle consistency loss, and anchoring. Those are the 3 basic components. So the way we evaluate this is as follows. Previous work for scene flow has trained their methods using a synthetic data set and a small amount of real world label data. Again, it's hard to label a large amount of data for scene flow because you have to label the motion of each point. Our method extends this by being able to also train in a self-supervised way on a much larger unlabeled data set. And so that will significantly improve our performance, as we'll see. So if you train only on the synthetic data, then you get about a 25% accuracy on this task. If you add the small amount of labeled data from previous approaches, then you get a 6% boost. But using our self-supervised approach, we can train on a much larger unlabeled data set and significantly improve our performance. We can also look at the different components of our system and see how much they affect the performance. So if we remove the nearest neighbor loss, we get a large drop in performance. And if we remove the cycle consistency loss or the anchoring, we also get drops in performance. So all three components are actually important for our system. Qualitatively, here you can see what the flow looks like. So we're kind of drawing flow vectors between points, and you can see it pretty well tracks this bicyclist as it's moving. It's not perfect. We didn't change anything in terms of the network architecture in this work, just the losses to enable self-supervised learning. So there's more recent methods that use different architectures that we think will further improve the performance. But here using the same architecture, we're able to get much better performance by training on unlabeled data with our self-supervised method. So to conclude this section, we use a self-supervised training method for scene flow prediction. We are able to then leverage large unlabeled data sets and thereby exceed the performance of supervised training that was done on a much smaller labeled data set. So that's the second part of the talk. And then let me know if there are any quick questions about that part. I see one question in the chat. Is the definition from scene flow that you project image pixels into a 3D environment? So it's actually the opposite. So the definition of scene flow is for every point in 3D space that was returned by a depth sensor, the scene flow is a 3D vector that describes the 3D motion of that point. If you were to take that 3D vector and project it onto the image plane, then you get optical flow. So optical flow is a 2D projection of scene flow. And then the other part is how do you get the visualization of the scene flows on the silhouette of the vehicle? So basically, that maybe you're talking about this visualization. So for every point in the red frame, we run scene flow to align it to predict where that point has moved in the next frame that we're drawing in green. And so if the vector is pointing in the right direction, it should match the corresponding points across frames, showing that we've correctly predicted the motion of each point. Okay, so I'll finally talk about the last part, which is about self-supervised 3D data association. So, okay, so here we're going back to the traditional tracking pipeline where we have objects and we're trying to track them across frames. So how is this traditionally done? Well, traditionally, we might use something like a Kalman filter to estimate a smooth motion of each point. And then if here's an object that we've been tracking, then in the next frame, we detect some objects and then use the Kalman filter to predict where we think that object will be in our current frame. And then we look at the distance between the predicted location of this object and the detections and use that distance to match the tracked objects to the new detections. So this is the traditional approach. More recently, people have started looking at the appearance of objects to help match objects across time. So if we have some object that we've been tracking, we can extract some 3D embedding for this object based on its point cloud So you pass the point cloud for that object through a neural network to extract an embedding, which represents the appearance of that object. And then we can also embed the detections in the current frame. And then we can look at the similarity of these embeddings to figure out which objects from previous frames match to the objects in the current frames. Now, the question is, how do we learn this 3D embedding to do this matching? Previous work learned it from label data, where you've labeled bounding boxes and labeled their associations and use that to learn the embedding. But we'd like to ask the question, can we learn this embedding from unlabeled data? So here's our approach for doing so. So the high level idea is we start with running a detector, and then we use a motion-based data association method like a Kalman filter. The Kalman filter will make some mistakes. So now we need to estimate the probability that's made a mistake and use that to weight each of the associations based on the uncertainty. And then based on these weighted associations, we can learn an embedding for the point clouds. So here's what that looks like. We have first run our Kalman filter to form some possible associations. And then we run a Hungarian algorithm, which is a standard approach for matching, for doing bipartite matching between tracks and detections. So each element in this matrix is the score of how well a track matches to a given detection. And so the algorithm has chosen, for example, that track 2 matches to detection 2. Now, what we look at is what's the score of the alternative possibilities. So for example, track 2 might have matched to detection 3 with a score of 18 instead of 6, so a little bit worse, or it might have matched detection 2 to track 3 with a score of 17 instead of 6. So you can look at the ratio of those scores to say, how confident are we in this match? And how close is this score to the score of the next best alternative? So based on the ratio, based on the ratio of this score to the next best alternative, we compute an uncertainty metric. And we accumulate those uncertainty metrics over every pair of frames across the frames that we are tracking. And we use these accumulated uncertainties as a weighting that we're going to use to weight this loss. So for matches that we're very confident, we'll weight highly, but for matches that we're not very confident, we'll downweight them in our loss so they don't affect our learning too much and don't mess up our embedding when we've made a mistake. So given these matches, we learn an embedding with standard triplet loss using cosine distance in the embedding space. The main innovation here is we're weighting the losses by this uncertainty. And this is all self-supervised. So if it were supervised, we wouldn't need to have any notion of uncertainty, but because we're operating the self-supervised case, we have to take into account the uncertainty that we might have made a mistake. Now, given these embeddings, we then combine the Kalman filter-based distance with the detection score with the score from the appearance embeddings in a logistic regression to actually match the objects across frames. This combination is done using logistic regression. This is trained with a small amount of label data. So we need a small amount of label data just for this step. But for learning the appearance embeddings themselves, we can learn from just unlabeled data. So we evaluate this using both single object tracking and multi-object tracking evaluation setups. And here you can see the main results. So our results are shown in light blue, and you can see we get better performance than the supervised approaches and almost as good performance as the Oracle. You can see the Oracle in this case, which is not actually perfect, which essentially means that we need maybe a better network architecture or something like that, but it's still encouraging how good our self-supervised method can be. And here you can also see the scores of incorrect detections on the left and correct detections on the right. So our method gives a higher score to the correct detections and this is without incorporating uncertainty. If we incorporate uncertainty, then the scores get even more accurate. So the scores of the incorrect detections go down and the scores of the correct detections go up, which is what you would want. So
David, we have about maybe 4 more minutes.
Sure, no problem.
We'll pass the
Yeah,
time.
so I'm just wrapping up here. So basically, to conclude this section, we've developed a self-supervised method for representation learning for 3D data association. Our method incorporates tracking uncertainty for robust self-supervised learning in order to handle tracking errors. And our method avoids the need for extensive manual annotation by making use of large unlabeled data sets and incorporating uncertainty in the cases where we've made mistakes. So so that's the last project that I'll be talking about. And this is just a summary of the 3 projects that I talked about today: active perception with light currents, self-supervised 3D scene flow, and self-supervised 3D data association. So I'll actually end here, and I'd be happy to take additional questions either now and also in the breakout room later.